My name is Eric, and welcome to this data review. Today, I have a super exciting case. It was one of the highest publicly rated notebooks on a recent Kaggle competition and walks us through an exploratory data analysis, short EDA, on a massive 50 gigabyte dataset. So if you like the video, give it a thumbs up and let's get started. The notebook was uploaded as part of the American Express default prediction competition that ran from May to August this year. So it just wrapped up about a month ago. American Express is one of the largest payment processors in the world, and they have this classic problem that given the history of statements of a set of customers, how likely is it that these customers are not able to pay their statements in the future? One thing I thought was really interesting about this is the data. So the data set has only 4 files, but has a whopping size of 50 gigabytes. Just the train data set alone is 16 gigabytes, and the test data set is about 34 gigabytes. So what's contained in this data set? All variables are labeled by D, S, P, B, and R, and they're just like loosely grouped into these different categories you can see here. We don't really know much else about the variables. They just have like these cryptic names, D_116, If you have ever done a loan prediction case, however, you will notice these are very typical features such as the rate a customer has gotten. What's the income of a customer? Does the customer own a home, or does the customer rent? What's the credit score, So you can think of these variables really like describing the customer and its financial environment. There's 188 features in total, so quite a lot. Out of these features, there's also a set of categoricals. Before getting started, I wanted to give a shout out to Ambros M, who's the author of this notebook. Ambros is a dual Kaggle grandmaster and one of the top 10 grandmasters for notebooks and discussions, as you can see here. In fact, this notebook we're going to discuss today is one of his highest rated notebooks. So I'm really thankful for his work. And if you like his work, definitely check out his profile on Kaggle and follow him. I'll make sure to post a link to his profile in the comments section. So I opened up the notebook in Kaggle's Jupyter environment. And while you can run the notebook from start to end, I noticed that every time I wanted to make a transformation, the Kaggle kernel would run out of memory and crash. At some point, I got really frustrated, and I just booted up my own SageMaker Jupyter instance. So this is a machine with 32 gigabytes of RAM and 100 gigabytes of storage. To get the data actually into the SageMaker instance, you can just download the notebook from Kaggle and upload it here into the Jupyter instance. And then you can run this little code snippet to download all the data fields as needed. Just make sure you put in your username and your Kaggle key from the Kaggle JSON file you are provided in here and just execute. This will run for about 30 minutes, download all the files, unzip it, and at the end, delete the zip files to clean up some storage. So the goal of EDA is really to build a good understanding of the data we are dealing with and its shortcomings, so we can at the end build a machine learning model on top of it. So we will now look actually through all the files, unpack them, look at the different features, categoricals, numerics, binaries. We will analyze the date column a lot. And at the very end, we will also discuss a denoising technique, which allows us to improve the data quality by removing noise that was artificially added for the competition. So let's get started with the labels. The label data set is actually relatively simple. It only contains 2 columns, a customer ID and a target column. The target column can either have 0 values or 1. Ambros tells us that 458,000 customers are in total in this data set, of which 74% have a 0, so these are the good customers, and 26% have a 1. These are the bad customers that will eventually default. Interestingly, the competition had told us earlier that the 0 class was actually subsampled. So in reality, they worked originally with 6.8 million good customers, which would have given us a 98 to 2% ratio. These are very unbalanced data sets. And there's different methods to actually deal with unbalanced data set. However, if you're Amex and you have a lot of data, the simplest is just to subsample the majority class and make the majority class closer actually in total counts. So one thing you actually want to do is you want to check if there's any non-values in any of the fields in your target labels. And this is quite quickly done with pandas is non function. But I quickly wanted to describe the syntax here, this any.any function, which I thought was kind of cool, So let me just quickly dissect and show you what this does. So if you apply is non to the train labels, what you will get is essentially just a Boolean array with false and true. If there's any non-values in any of the fields, it would be true, and otherwise it is false. To collapse now these 2 columns into just 2 values, you can apply the any function, and it will tell us essentially that neither columns have a non-value, so both are in total false. You can apply now any again and essentially sum over these 2 false, and it should give you also, you might have guessed it, a false, right? So just by applying is non, any, you can just quickly check if any of the values are non. If some of the values would be actually none, we would have to do a little bit more work to investigate which ones are really none. The second thing we want to check is if any customer's IDs are duplicated. They shouldn't be really, right? So a customer should only be in the 0 and the 1 class, but they shouldn't be in both classes. And you can use the duplicated function in pandas. Again, this would give you a Boolean array, which true and false. And by applying any, it essentially just sums it up to a false. So by actually printing these two statements out, we nicely see that A, there's no non-values in the target or customer ID columns, and B, there is no duplicated customer IDs. The next thing we do is building a quick statistics pandas data frame. And we simply just take the counts of the target column to see how many zeros and how many ones there actually are. We then put this in a data frame, we label everything properly, and you get this absolute column here. So there's 340,000 zero values and about 118,000 one values. These are exactly the numbers that Ambros has been telling us here on the top. So he has already a little preempted this result. We can also calculate the relative values, the percentages, by dividing the absolute values simply by the total lengths of the train labels. And what you will see is that it comes out to about 74% versus 26%. You can do then some arithmetic to calculate what this upsampled, what the actual original data would have looked like, and you would have gotten probably 6.8 million customers in total, and this 98 to 2%. The right side is really not relevant for this competition. It's not like you're going to do anything with it, but it's still interesting to know how big the actual non-subsampled data set would have been. So let's talk about the other two data sets, the train data and the test data. And I wanted to quickly draw your attention actually to the file type we're going to use here. It's an FTR file, also known as a feather file. This is a very interesting file type. It's a binary file type. And with that, it's actually compressed, so it's usually smaller than CSV. It's also more efficient to be imported because it is already binary. There's something else you might not know, actually. So this feather file was created by another Kaggle user, and the float number precision was reduced from 64 to 16-bit. This is actually a very nifty trick. If you have a very large data set and you cannot fit it into memory, but you somehow want to analyze it, you want to use pandas, you don't want to go to something more bulky like PySpark, for example, you can actually reduce the precision and then import things into pandas. The first time I read about this, I was a little bit like, doesn't that really throw away information, and isn't that dangerous? Absolutely correct. You should be very, very careful doing these things. From my understanding, the way this is approached is you downsample the data, you do your feature engineering, you build your machine learning model, and you see actually what kind of results you're going to get at the end. If the results are totally terrible, you're either a bad data scientist or the downsample data is really not that good. However, if you do actually get good data, that means that you might not need this super high precision, And you can always essentially increase the precision at a later time and steps and see if you then actually get better results. So it's a little bit like, how else are we supposed to do with this data set? So let's downsample it and let's see what kind of results we're going to get. So I imported the train and test data here, and you're going to see the output quite here. The data looks very similar. The train data has 5.5 million rows, while the test data has 11 million rows, so it's roughly twice the size. Both data sets have almost exactly the same number of columns, 191 versus 190. And you might have already guessed why the training data has one more column. In fact, the extra column is the target column we've just discussed on the top. So the user who made this feather data set actually already joined this target column in for us, so we don't have to do that at a later time. You will also notice that most of this data is obfuscated. It's normalized data, there are no labels whatsoever, and all of them seem to be numerical of some sort, with the exception of column S2. S2 is indeed a date column, and this will be identified as a column that gives the statement date when a statement was being sent out to a user. So we're going to spend a bunch of time actually analyzing this. So the first thing we probably want to look at is, what is the range of statements in that column? So we can just use the min function, the max function. We can also check if there's any non-values in it and conveniently print it out for the train and test data set. So one of the things I really like that Ambros does, he always does both things at the same time for train and test data because they are so similar. Why would you want to do that? Well, we're going to find some differences between these two data sets, and these differences are actually quite important. So it's really nice to always do this together so you can identify the differences. So what's one of the differences? So you see that the minimum date in the S2 column in the train data set starts in March 2017, and the maximum is March 2018. So we have about 1 year range, 2017, 2018. This is the training data. However, in the test data set, you will notice that the minimum date is April 2018 to October 2019. So it's actually at a later time. And that's really interesting because that means we're really using past data to predict data in the future. And it's going to be very difficult actually to do some kind of like economic cycle predictions through that, because we have to use the 2017-18 data to predict something in 2019. If there were changes from 2018 to 2019, for example, inflation, for example, or the Fed would increase the rate, we could not really predict that with this data set. We can also look quickly at the size of the data in memory, and we'll find that the train data is about 2 gigabytes and the test data is about 4 gigabytes. So quite large, right? There's a couple of consequences from this. One consequence is that you probably want to be careful keeping all that data in memory. And every time you do some sort of transformation or aggregation, you might want to actually delete the data later on to keep your memory clean. The other thing is actually to be memory more efficient, we don't need to train and the test data in one data set like we do here. There's no need to actually have the test data in the same kernel. And in fact, Ambros is suggesting even to have 2 notebooks, one for the train and one for the test. You take the train to train your machine learning model, you test it on your train data also. And once you're happy with your machine learning model, you build a second notebook in which you fit the test data, and then you submit your results to Kaggle. So let's look at the info output on the training data set. The .info command is actually something I use quite frequently really early on in an EDA because it tells you what data types have been actually imported. We can see that most of the data types here are actually floats. There's a few categoricals also in here. Then there's a datetime column number as 2, and then there's a custom ID, which is an object column. If you imported this from a CSV file, it's very unlikely pandas would have auto-detected all of these data types. So it's kind of paramount to run this command quite early on and make sure pandas has set the right data type. There's another thing we can glance from here. The training data set had about 5.5 million rows in total. And you can see actually that some of the rows seems to have a non-significant number of null values. So for example, this column here, D42, has 791,000 non-null values, which means it has over 4 million null values in that column. And we can find lots of other columns like this. So one big aspect actually of EDA is also investigating which columns are mostly none and we can throw out, which ones are partially none and we might want to interpolate, and which ones are really good columns with very few none values. Why is this important? Some machine learning algorithms are really can't deal with none values, And in fact, there's also pandas functions and NumPy functions that really don't like working with none values. There's some machine learning models I recommend starting with, like XGBoost, for example, that are relatively immune to null values. So it's less of a problem for those. Next, we want to analyze a little bit further this S2 column, the date column, because this tells us essentially when a customer has gotten a statement. So we're just going to make a couple of graphs and going to interpret those. The first thing we want to look at is the number of unique customers ID in the whole data set. And we're going to again split it into train and test data set. We can just use customer ID, value counts, to get that. So let me just quickly explain what this does. So the first value count just counts how often a customer ID shows actually up in our data set, right? So customer with this ID shows up 13 times. A customer with this ID only shows up 1 time. What happens now if I apply value count again on this one? It will actually count the number of values that show up in the second column and summarize it to you. And it will tell us, well, from all the customers, 386,000 have gotten show up 13 times, 10,000 show up 12 times, and so on and so forth. So when we visualize this in pie charts, and kudos here for Ambros to using a pie chart, it will look something like this. And this is actually quite interesting because you can immediately tell that about 80% of all the customers have gotten about 13 statements, over the period of the train data and over the period of the test data. However, there's about 20% of customers which have gotten 12 or less statements. This is here. This is quite important, right? Because if you want to build a model that requires 13 statements to make a prediction, well, you're not going to do a very good job for all the customers that have less than 30 prediction. It turns out when you look actually at some of the machine learning models being built, most actually of the users aggregate over all these statements, so it's not so relevant anyways. But if you wanted to do, for example, some time series stuff, you're going to be at a weaker position for the customers that haven't gotten as many statements. So very similar, we're just going to essentially plot a histogram of when customers have gotten their last statement. And we'll find that in the training data set, almost all customers have gotten all their last statements in the months at the end of the training data set, which is March or April. You can see it's actually relatively even over this period. How does it look for the test data set, however? It looks quite interesting. In the test data set, customers have gotten their last statement in 2 batches. There's one batch, which was given in April, May 2019. And then there's a second batch, which is October 2019. And this seems a little bit surprising. So train data was all given at the very last months of the training data set. The test data, however, is split into 2 test data sets. And we'll come to that in just a second. Another question we can ask is, how much time has an average passed between the first and the last statement? And we can also make a quick visual about this. And we're going to find that for both train and test data set, the average time for most of the customers is about 12 months or 365 days. You can see this here, with some customers obviously straggling, some having a little bit more, some having a few days before the last independent data set. So why is the train and test data split up like this? Why does the test data look like there's actually 2 test data sets? So let's label the data sets we found by when a customer has received their last statement. And we can actually see that there's indeed 3 data sets. We have the training data set with all customers having gotten their last statement in March 2018. We have a first test data set with all customers having gotten their last statement in April 2019. And we have a second test data set with all customers having received their last statement in 2019. And Ambrose nicely labels those as training, public leaderboard, and private leaderboard. What does that mean? If you've never done a Kaggle competition, when you upload your results to Kaggle to compare to the ground truth, you are provided with 2 scores. You're provided with a public score, which is typically available immediately, and you're provided with a private score, which is not available until the competition is over. And why does Kaggle does it that way? Well, it's relatively simple. If you upload your results to Kaggle, Kaggle gives you feedback on the score. You might be able to manipulate that score by changing the data, and without actually changing your machine learning model. You could just type in random numbers, upload it, and see if that improves the score. However, because you can't change really the score on the private leaderboard, that doesn't really help you if they don't disclose some part of the score, So that's why we have 2 test data sets, public and private, and we can nicely visualize this here. We have nicely visualized this here. But there's other consequences from that. And Ambrose talks about it really nicely. So you can now look actually of what the distribution is of the features we are given in each of those data sets. So imagine you had a feature that only existed in the green or in the orange one. That feature would be completely useless because we can train on it in our training data set. Similarly, imagine there's a feature that only exists in the blue data set, but not in the orange or in the green or neither. That would also not be very useful because that feature can't be used for actually then fitting the training data set, the test data set, and uploading the scores to Kaggle, right? So by segmenting the data sets out very nicely into these 3 types, we can look at distributions of features in each of those and eventually identify some features which we can already rule out for being useful. And that is also what Ambrose did. He didn't tell us exactly how he found those features, but he's looking at 3 features here. I want to just briefly talk about them. B29 is exactly a feature that does not exist really in the training data set. It's mostly null values that exists very little in the public leaderboard data set and really only exists in the later half of the private leaderboard. Is that really surprising? Are they trying to trick us here? I think this is mostly like just happened naturally. If you, for example, imagine Amex is introducing a new variable they want to track for their customers, but they didn't introduce that variable until 2019, and they weren't then really able to backfill all the other variables for the earlier data set. You might have exactly with the data set like that. You might have end up with a variable that only exists from 2019 and onwards, but not prior. However, most of the other variables, from what I can tell and what Ambrose can tell, seem to existing in both data sets. So for example, S9 is another example. It exists sufficiently much in the training data set. It exists sufficiently much in the public leaderboard and also in those. What Ambrose doesn't tell us is how do we automate this process? There's over 188 features. Are you just gonna like print them all out and just gonna look through it? So that is, I think, a little bit left as an exercise. Can you write a function that measures, the number of null values of a specific variable in any of these three data sets, then you run it over the 188 features, and then you sort it by the ones that seem to have been the largest unbalanced. You will probably find B29 at the top with that. So let's move on from the date column, and let's look at some of the other features. Let's start with the categorical features. The Amex competition actually tells us which features are categorical, and they're shown here as a list. And what we're going to do is we're going to create a histogram of these features to show how many categories show up in each feature. But then we're also going to segment it out into how many of those show up for the target 0 customers and for the target equals 1 customers. You can do this quite efficiently just by writing a for loop and essentially printing those out all together. And you're going to get something like this. So let me explain what you actually see here. So let's start with this B30 feature, which is one of the categoricals. You can see that the B30 feature has 3 categories: category 1, 0, 1, and 2. And it may have some NaN values, although it doesn't look like it has any NaN values here. At the same time, you can tell that the 0 category in the B30 feature is actually more frequent in the target 0 column and less frequent in the target 1 column. And the same is true, for example, in B38. B38 has 7 different categories, all the way from 1 to 7, maybe a few NaN values. And you can tell that the category 1 and 2 prefer the target 0 customers, so there's more of those. And then category 3 to 7 prefer more of the target 1 customers. What might this be? For example, that could be the question if they own or rent a home. So you could tell, if they own a home, that probably prefers customers that can pay off their bills regularly. Well, if you rent a home or you live in a trailer or something, you might be less likely to pay off your loans. And similarly, these higher categories have the opposite. So they seem to be more correlated with customers that can pay off. So all we're going to actually gain from this is that we can tell that the categories and the categoricals seem to have all some relationship with the 0 and the 1 customers. So they're very likely good features to be used in a machine learning model. There's like one feature where you can already tell that might actually not be a good categorical. And then this is this D116. Again, we don't know exactly what categorical it is, but it's interesting that it first of all has only 1 category. And second of all, that category seems to be equal on the target 1 and the target 0 one, So the predictability for this feature for either category is probably not very high, And also that it is lacking essentially another, this is quite telling. So this is probably a feature I would actually remove from the analysis. The dataset also has 2 binary features, B31 and D87. And similarly to analyzing the categoricals, we can look at the distribution of the categories, each of those feature with the target 0 and target 1 customers. And we'll find actually that the binary features seem to be, very, very unbalanced. So for example, B31 seems to be mostly favoring target 1 customers and has only most of the target 1 customers in category 1. D87, on the other hand, seems to be mostly NaN, and very few values are actually 1.0. So very similar to the categorical feature we saw earlier. That is a very good candidate, which we might want to actually drop from the dataset. And lastly, we want to talk about the numerical features, which of the dataset has the most. So we write a for loop to look at the distribution of all these numerical features to get a quick glance on of like what kind of distributions we can expect. This actually runs quite a bit because you have to print out over 140 graphs, but we can now nicely scroll through all the numerical features and look at them. And you're going to see some maybe exponential type functions. You're going to see some more spiky functions. You're going to see some exponential log normal distribution functions with like a spike at 1. So there seems to be some kind of outliers. And then you see some features that seem to be more like binary, which only have values between 0 and 1, So this is quite a mess, to be honest, for all the, features that look fairly normal distributed or look like they represent some kind of distribution. I would probably do some kind of Cox transformation to make the features more normalized. But because we have so many outliers, it's a little bit tricky to say immediately what you want to do. And we probably would want to spend a little bit more time really looking into this. It turns out, if we come to the last section, we kind of know actually where some of these spikes are coming from, and we can get rid of those. So let's talk about that. Yeah, and this brings us already to the last section in our notebook. In this section, we will learn how artificial noise was being added originally to the data set and can now be, in some cases, actually be removed to improve the quality of the data. The less noise, the better for our machine learning models. But at the same time, it also helps us to drastically reduce the file size again. And I'll explain this in a little bit. But first, I wanted to quickly talk about this function here that actually allows us to work with these originally really, really large files. If you remember, for most of the analysis, we've used a data set where the precision of all the float numbers had been reduced to 16-bit. And for the noise analysis, however, we want to work with the original data, which has the highest precision, 64-bit. But you remember, like, the training data set alone was like 16 gigabytes. So in pandas, there is actually a parameter called use columns, which allows you, when you import a data file, to only select out specific columns, to obviously reduce the size of the data in the memory. Unfortunately, that can't be used here because that use columns required all of the data to be in memory at first. So pandas would have to read the full size into memory before it can drop columns. However, pandas has another parameter called chunk size, which allows you to read CSV files in by rows by rows. And we're going to do here 1 million rows at a time. Remember, the training data set had about 5.5 million rows. So we need 6 chunks in total. And the basic idea is chunk up the main file, read in each chunk, and then only select a few features and drop all the other features. And then you repeat that for each chunk. And at the end, you stitch all the chunks together, and you're only going to end up with essentially the columns for the features you were interested in. In this particular case, we're only going to look at 2 features, B19 and S13. The basic idea is that the data had been very likely was very likely modified by Amex to be anonymized. And one way to anonymize data is usually by adding noise and doing a bunch of transformations. So a typical function to anonymize data is, for example, shown here, where you take your data, let it be float, you subtract first the minimum, then you divide by the maximum, then you round the data, in this case here to 2 precision, and then you just add some raw noise. In this case, it's just some random uniform noise. And this gives you your output data. The idea is here that if you kind of know what kind of anonymization function has been used, you might be able to reverse engineer some of this and maybe get rid of some. So we can't really undo the rounding because rounding will throw away data, and we're not going to. We might also not find out what the minimum and the maximum of the data is. However, there is actually a way in some instances to remove the uniform noise. But to make this a little clearer, I've actually just used this function and built a sample data set. I'm just going to randomly sample a couple of integers between 0 and 5. We're going to sample 100,000. And then we're going to apply this anonymization function. So we subtract them in, we'll divide by the max, we round, and then we add some random noise of specific kind. And then we'll show how this can actually be reverted to some extent. So the data frame looks something like this. These are the simulated integers here as floats, 2, 0, 4, 4, 0, 1, 3. So this is random. This is an anonymized data, simulated plus anonymized, And you will notice already that these originally integer numbers are now actually all floats. So 2 becomes 0.5 and 0 becomes 0.00 plus some noise, 4 becomes 1 plus some noise. But so looking through all of this, right? It seems immediately that there isn't really any clear pattern, And in fact, this 2 is 0.505 and is different than this 2, which is 0.503, So these are actually 2 different numbers if you would equate them, although originally they were really the same number. But you can make an observation. That observation is that these numbers seem to be only differ by some precision, So for example, if I compare this 2, and this 2, you will notice they all are 0.50 and then some other numbers, So by essentially rescaling this number and just cutting down the precision, you can find a one-to-one mapping between all these numbers. So in this case, it's actually quite simple. You just multiply by 100, and then you take the floor, which is just rounding down, And you're going to find that, you know, this 0.5 is turned into 50, this 0.5 is turned into 50, and this 0.5 is also turned into 50. So all of a sudden, it seems like we'll almost get our old hierarchy back. Instead of floats, we now have to deal only with integers. There's a very clear mapping between 2 and 50, 4 and 100, 0 and 0, and so on and so forth. So we literally have denoised our data. This is great. That doesn't always work as easily, and it's not always clear that this 2 maps to a 50. It could also map to a 51 or a 49, for example, in some instances. However, even though this mapping might not be perfect, it's still better than using this noisy data, because this noisy data, these are actually also 2 different numbers. So it doesn't matter that at the end the mapping might not be perfect. So now I might say, well, but you have, like, you know, simulated the data, so you knew exactly what the transformation for the noise was, and then at the end you did the mapping by essentially just multiplying times 100 and taking the floor. But how can you do that actually when you start off with a number and you don't know exactly this? Well, one way to do that is by looking at the histograms, and I'm going to show you this exactly on the simulated data again. So I'm showing here a histogram. We know all values of this simulated anonymized data are between 0 and 1.1. It's because we generated numbers between 0 and 1 that were all normalized, and then we added some noise of length 0.1, right? So 0 and 1.1 is kind of the maximum. So I'm going to make 11 histograms right now here. You know, this is the first histogram all the way to the 11s. And you will notice that a couple of these are empty. So there's ranges between 0 and 1 where there is no data essentially. And then you find these distributions here, right? Between 0 and 1.01. You find here between 0.75 and 0.6. You know, so you can very clearly see that the anonymization in this specific case, in my trivial example, just having 5 numbers, you know, and then adding noise, is not working really well, because, you know, all I have done is essentially I've taken my number and spread it out a little bit, made it a little wider, you know. And it's now very easy to see how you can essentially remove the precision and collapse all of these histogram bars into just one bar, and you're going to recover something very close to what you had originally. Again, it's still scaled, it was still rounded, you don't have recovered all the information, but you've made the problem much, much simpler. Instead of dealing with floats, you're now dealing with integers, and you know exactly that it's only like 5 integers in this specific case. It becomes essentially a categorical variable, while before it was a numerical one. And on top of it, you also remove noise, which makes obviously your prediction much, much better. So it turns out that some really clever guys at Kaggle have indeed done this for a couple of features. And let's look at this B19 feature, which looks actually not too different from what we have here, right? You can look at, again, the 11 histograms sliced between 0 and 1.1, and you're going to find there is like something around here. This is very likely a 0, you know, and something like here, this was very likely an 8, you know, and this was very likely a 9. And because none of these histograms really overlap, you can really do the same principle here, multiply times 100 and take the floor, and really essentially get almost completely rid of this noise. Yeah? I want to show you one example where this actually doesn't work. So if these histograms were like much denser and would overlap, you can't just multiply by a number and take the floor. And there's actually an example here too, you know. So again, the same function. It's the S13 categorical. The 0 looks nice, you know. The 4-ish number looks nice. The 28 number looks nice. But there's actually one example here between 0.68 and 0.7 where you can see that these histograms are overlapping, you know. So you can't just, in this case, you know, truncate the noise and say, well, this is now number 68 and this is number 69, because some portion of 69 actually overlaps with 68. So you really, what you have to do is you have to be a little bit more clever and actually do some kind of deconvolution, which is still possible, you know. Luckily, you don't have to go through all of that if you want to work with a data set, you know. There is a Kaggle user called Radar who has done this for all the 188 features. And he has then nicely also provided the data set himself to the community, you know. I thought this was really, really interesting. I highly recommend looking at his notebook and how he does it, and especially also how he does it for the numbers that have overlapping histograms, you know, how you can actually then do this deconvolution. All in all, I wanted to say, I thought this is really clever, this section. I really enjoyed learning about it and, you know, learning something new in my brain. It's a very Kaggle type kind of thing. I don't really know if you would ever do this really at home, because what this requires really is somebody must have given you a data set and anonymized it. And then obviously de-anonymization is kind of like, I mean, if it gets you more points in your Kaggle competition, of course you can do it, but it's also a little bit defeating the purpose in a way. It's just clever reverse engineering of somebody who really wanted to obfuscate the data. If the Amex people they could have designed this anonymization technique actually a little bit more robust and could have adjusted the noise based on the type of data you had. And in such a case, you would have very little chances actually recovering any of that, but because they seem to have used a standard anonymization technique and just applied it to all variables, there's definitely some for which you can denoise things. One interesting aspect which I thought was really funny is, and some Kaggle user actually noted, the reason why the data sets are so large, that 30 gigabytes or 50 gigabytes in total, is mostly because of the artificial noise being added. And this is kind of like really interesting. A lot of the variables are actually categoricals or integers, so their memory footprint is not that large. But because you're now adding noise at a high precision, all of those features become float 64 bits. So all of a sudden you have turned 188 features, of which maybe half of those were actually integer 16 or integer 8 or whatever. You've now turned them into float 64, and you've massively increased actually the size. So some Kaggle user was just saying, oh yeah, so the data set is really mostly noise, the size of the data set. So by denoising it, you can also remove the size of the data set, which I thought was really, really cool. Yeah, so this brings us already to the end of the case. I hope you enjoyed the case as much as I did. I learned definitely a ton, learned about feather data sets, learned about reduction of precision to make large data sets smaller. I learned about how to deal with like time data, and obviously we also learned about this really cool denoising technique. You will see when we talk about a few machine learning projects on this specific data set that most of these methods are actually being utilized. And in fact, the community seems to reutilize what other people have come up with. So this radar data set that is being denoised is already commonly used now in a lot of machine learning projects. So you have a very nice baseline. On a personal note, if you had to design such an EDA all yourself from end to end, including the noise, this would have been a many-week probably project. And oftentimes in reality, you don't really have that much time to work on things. It's still very cool though to see what you can do when you crowdsource knowledge about a data set and then put it together. It is also true that Ambros did not design this EDA notebook in one day. You can actually see that there's a version history, and this is already version 6. So over time, he has actually added more sections to that notebook. And in fact, this is also how EDA works a little bit. If you build a machine learning model, you might learn something about your data, which you didn't know before because you spent more time in it, you learned some of the nuances. So you then might include this later in your EDA again. So it's not like EDA is really like a finished thing. But this is also one of the difficulties in general with EDA. You can spend a lot of time on EDA. I think one of the key takeaways from here is definitely spend the time to understand the null values, definitely spend the time to think about how to turn a large data set into a small data set. That gives you a huge advantage, makes things much, much quicker. If you had to read in every time like a 30 gigabyte file, just if you want to do some basic stuff, you're going to sit here forever. So I really, really recommend taking a few things and the other things more as learning for yourself. Or if you want to participate in a Kaggle competition, you're also more than welcome to repeat all of these techniques yourself, of course. And this is it for today. Thank you for watching, and don't forget to hit the like button.